come from? So let's say we have our function. We're going to call this a generic, call this x1, no, call it xi. This is xi plus 1. Now what I want to do is, like everything we do in Calc 2, we're going to break it up into little pieces, and then we'll add up all the little lines, and then we'll get an approximation of the arc length. Then we take the limit as n goes to infinity, where n is the number of lines, and the closer we get to infinity, the bigger n is, the better our estimation is. So if we take the limit, it will give us the actual length. Now, before I play with the formula, I want to remind you of a theorem that you may or may not remember. So let's say this is A and B, and I'm going to draw a line between the two. Looking for a different color pen. Of course, I don't have one. So I'm going to draw a line here. Now, the slope of that line is equal to f of b minus f of a over b minus a, where this is the function f of x, so this is f of a, this is f of b. Now the theorem states that there exists a c somewhere between a and b where the slope of the curve at that point is the same as the slope between a and b. As long as a and b, the curve is smooth between the two. So it actually looks like we have two possibilities. So what the theorem says is there exists c between a and b such that f prime of c is equal to that slope. So that I need that for my theorem. So let's go back up. Go back over here. So I have xi plus 1, and this is my function f of x. And my f of xi and all that. Now, the distance between these 2 points is the square root of xi plus 1 minus xi quantity squared plus f of xi plus 1 minus f of xi. Those two are squared. Now I'm going to do some algebraic manipulation so I can play with this. I'm going to suck this thing out. I'm going to divide both terms by xi plus 1 minus xi quantity squared. So when it comes out, it will be xi plus 1 minus xi, actually be the absolute value of that. And then in the square root, I'll have a 1 here, and here xi plus 1. Well, they're both the f and the xi's are squared, so I'm just going to go ahead and put that square to both of them. Maybe that's kind of a mess. So here's my difference in y's over my difference in x's. This is the slope between these 2 points. So by our theorem over here, there's something in between these two where the derivative is equal to this. So we can call this like xi star. So I have the square root of 1 plus f prime of xi star quantity squared, and then times this guy, which is our delta x. That's the width of our interval. So to find the estimation, we would take the limit as n goes to infinity of the square root, summing up, the square root of 1 plus f prime of xi star squared times delta x. And then to get the better estimate, or the exact estimate, I've already done the limit. I already did both parts. Okay. As I goes from 1 to n. And this, you know, is equal to the integral from a to b. This becomes square root of 1 plus f prime of regular x squared, and the delta x becomes a dx. So this is my arc length formula. Now for the surface area, we're going to assume we rotate this about the x-axis. We can actually rotate it about both, but we only do one in this class. We only generate one formula. So rotate so what we have, okay, there's this. So you see we have a little cylinder here. And the area of a cylinder, or the surface area of a cylinder, is 2 pi r/h. Well, in this example, my height is my arc length, and the radius is the distance from here to here, which is just f of the function, or f of x. So the surface area will be the integral from a to b. I need a 2 pi. Let's go ahead and throw that out front. My radius is f of x, and my height is the arc length, which is 1 plus the derivative squared, all square rooted, dx. So there's my surface area formula. So let's say I ask you a question. Typically I'm going to ask you what the surface area of something is, or what the perimeter is. So let's say I give you f of x is equal to sine x, and I want, oh, let's be silly, I want g of x to equal cosine x, and we only want it in, x has to be between 0 and pi. So let's draw this. That's your sine wave between 0 and pi. And your cosine wave, oh, that goes under the axis, so I can't do the rotation. But we can do arc length. We can do, yeah, we can do arc length, or the perimeter. So here's my region. So if I want the arc length, I need to go along the top and along the bottom. Sine and cosine meet at 45 degrees, or pi over 4, in the first quadrant where they're both positive, and in the third quadrant where they're both negative. So this is 1, 2, 3, 4, 5 pi over 4. So for my arc length, I would have the integral from pi over 4 to 5 pi over 4, the square root of 1 plus f prime of x squared, plus the square root of 1 plus g prime of x squared dx. And give myself more room. Up here, f prime of x is cosine x. G prime of x is negative sine x. That negative is going to be squared off in a second, but that's okay. So f prime is cosine x. So filling in the details, I have the square root of 1 plus cosine of x squared dx, plus the integral of 1 plus negative sine x, but negative squared is positive. So 1 plus sine x squared dx. Oh, I didn't want that one there. You could do the, also have done this as two integrals with dx in both of them, but there's your arc length. Now, for surface area, I need different functions. How about we use f of x equals x cubed, and g of x is the square root of x. X cubed looks like that. X squared, or square root of x, looks like that. At this point, they match it. They connect at 1. So for this, our integrals will go from 0 to 1. I need the derivative of f and the derivative of g. We know that's x to the 1/2, so the derivative is 1/2 x to the negative 1/2, or 1 over 2 square root of x. So to get the surface area, when we rotate this thing around, I really don't want to draw this. We have an outside surface area and we have an inside surface area. So we need to add these two together. So the surface area, we have to deal with the f1. So that is 2 pi integral from 0 to 1. My function is x cubed. There's my r. My h is 1 plus 3x squared squared dx. Plus, now I'm dealing with the inside, 2 pi integral from 0 to 1. My function is the square root of x times the square root of 1 plus 1 over 2 square root of x, quantity squared, dx. And I could have written this as one big honking integral. I could have said 2 pi integral from 0 to 1 dx. Almost stuck it again. Either way's fine. So this is how you get use the arc length and the surface area. I will not on the test make you do these integrals because they tend to be kind of gross. But if you can set them up, that's the first step. So that's how you do arc length and surface area.